Hello everybody, this is Mikael from AUA and we're continuing our 21st lecture on probability. Today we're going to talk about discrete random variables and their characteristics. So up to this point we consider several examples of random variables and we will consider a lot. Some of them were taking just discrete values like the number of customers, number of goals, and some of them were taking any real values from some interval, like the lifetime of USB memory stick, or lifetime of a person, or lifetime of a light bulb, etc. In fact, the universe of all random variables can be divided into 4 groups. So we have 4 types of random variables. Discrete random variables, continuous random variables, singular random variables, and finally the mixture or sums of these 3 types of random variables. Fortunately, in our course we will just consider only discrete and continuous random variables. We will not study singular random variables. We will leave that for some advanced probability courses. And in fact, any practical random variable you will meet will be either discrete or continuous, or maybe some of that discrete and continuous random variables. So we will stick to discrete and continuous random variables. So today we're going to talk about discrete random variables. So I want to give the definition of discrete random variable. Now assume x is a random variable, define it on some sample space omega. So we are doing a probabilistic experiment. Omega is the sample space, the set of all possible outcomes, and x is a function from that omega to real line. The definition of the discrete random variable is the following. We say that random variable x is discrete if the range of x, which is defined to be the set of all possible values of x, the set of all values that x can take, is finite or countably infinite. So the range of x is the totality of possible values of x, and if x is discrete, that x can take only finite or countably infinite set of values. If x is discrete, then we can write the range of x, the values of x, as a sequence of values x1, x2, x3. Maybe this sequence will be finite sequence or infinite sequence. In that case, that will be a denumerable countably infinite set. So, some examples of discrete random variables. The first example is the following. So, sorry, I need to take that pencil. Okay. Now, x is a number of heads when tossing 5 coins, or just tossing a coin 5 times. Is it discrete or not? So to answer to that question, we need to think what are the possible values of x, the number of heads when tossing 5 coins. So x can be either 0, so no heads at all among that 5 tosses, or x can be just 1, meaning that I have just 1 heads and 4 tails, or x can be 2 heads, 3 heads, 4 heads, and finally 5 heads. So x can take only these values. So the number of possible values of x is finite, so x is discrete random variable. So this is a discrete random variable. Okay, so the next example is the following. So y, let's denote by y the number of children in the randomly chosen Armenian family. So if omega is the set of all Armenian families and small omega is just a particular family chosen at random, then y omega will be the set, the number of children in that family. Okay, so okay, what are the possible values of y? Y can be 0, so no children at all in that family, or they can have one child, or they can have 2 children, etc. Well, in fact, we can stop somewhere here, or we can assume that this is infinite. That is a matter of taste, of course. Okay, so let's move forward. Z is the number of accidents, car accidents today in Yerevan. So Z can be anything from 0, hopefully this is the case. So no car accident today in Yerevan, or 1 car accident, 2 car accidents, etc. Maybe up to 1 million car accidents today in Yerevan. So Z can take only finitely many values. That means that Z will be a discrete random variable. Usually people are assuming that Z can take any number from 0 to infinity for simplicity. Of course, the probability that Z will be very large is 0. Okay, so we have seen that X is a discrete random variable, Y is a discrete variable, Z is a discrete random variable, and next random variable is the claim size for today for one of the insurance companies. So the claim size can be, say, T can be 0 because no car accidents happened today, or T can be 10.1 million, or T can be 12 million, etc. So it is clear that T can take any real values from some interval, from say 0 to 10 to the 4, say calculated in millions of Armenian drams. In fact, you can argue that not all values are possible. So if I will take some irrational value here, T cannot be that irrational value because we are not using irrational numbers in our countings. But the life will be much easier if we will talk about all possible values from some interval about discrete values. So in this case, T is not a discrete random variable. It is taking any values from 0 to 10 to the 4 millions. So T is not a discrete random variable in this case. The next example is the following. So the next example is the Dow Jones Industrial Average Index closing value today. So let me show that in my browser. So this is the Yahoo Finance web page for the Dow Jones Industrial Average. What is the Dow Jones Industrial Average? It is the average price of 30 very important, very large blue chip companies in US, including say Facebook, Amazon, Google, etc. So this is the average price, and the market is closed. US market is closed. It will be open in 4 hours, and this price will be changed, and we do not know what will be the closing value of this Dow Jones Industrial Average. So this is a random variable, and this can take any real values from some interval, well, close to this value, 21,000 point something. So U will not be a discrete random variable. It can take any values from some interval. Okay. The next example is the number of page clicks or search queries in Google. The number of page clicks for today, say, it can be 0 or 1 or 2 or 3, etc. Practically up to infinity. So we can take the values from 0, 1, 2, so non-negative integers. And because the number of non-negative integers is the numerable, countably infinite, we will be a discrete random variable. The next example is the number of grammatical errors in my lecture slides. The probability that V is large is not so small. So W will be another example of a discrete random variable, because W can be either 0, the number, we are talking about a number of grammatical errors. W can be 0, 1, 2, up to some millions maybe. Okay, and you can give a lot of examples of this type of discrete and non-discrete random variables. Try to give some. Okay, so we encountered different random variables, and most of the examples of our discrete random variables were counting something. Say the number of goals, the number of page clicks, the number of search queries, the number of app downloads, the number of infected persons, the number of cars that will pass through Bahramian Street today, the number of successes in repeated trials, experiment, etc. But not only counts are discrete random variables. So discrete random variables can represent also other types of phenomena. Let me give an example. The example is to consider the darts game and let our random variable x be the points score I will get when throwing a missile. The sample space for this experiment, omega, will be the dartboard. It is two-dimensional circular region, and an outcome is the point where my missile will hit the board. So omega itself is infinite. In fact, it is non-countably infinite. It is continuum, but the range of x will be finite. And let me give the picture. So this is from Wikipedia, from the darts game page. These are the scores for our darts game. So let me take the pen. If I will hit here, I will get 0. So this is the score. If I will hit here, I will get 0. If I will hit here, if my missile will hit here, I will get 2 points. If I will hit here, this is the bull's eye, and I will get 50 points. If I will hit here, I will get 25 points. So the possibility where I can hit the board is infinitely many, non-countably infinitely many. I can hit here, 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 and the set of all possible points is very large. But the possible values of x, my points I will gain after one hit, is finite. I can get 0 points. I can get 1 point if I will hit here or there. I can get 2 points, etc. and up to 60 points. So despite the sample space is very large in the sense of number of elements, it is non-countably infinite. It contains non-countably infinite points. The possible values of our random variable is finite, so x is a discrete random variable. Okay, so let's move forward and talk about the general case of discrete random variables. So if omega is discrete, so if we have just finite or countably infinite outcomes, then any random variable defined on that sample space will be discrete. But if omega is not discrete, then X can be discrete, as in our example of the darts game. From this point on in this lecture, we will forget about our omega sample space and just consider the possible values of X. We will not talk about for which omega X is taking that particular value, but we will talk about what is the probability that X will take that particular value. Okay, now characterization of our discrete random variables. Assume X is a random variable and x1, x2, x3, etc. are all possible values of our random variable X. And the function p of x defined by the probability of x taking the value that's small x, so x is our random variable and small x is any real number. This function is called the probability mass function of x, so PMF of x, probability mass function. In fact, this probability mass function will be 0 for any x not in this set. So if x is not among x1, x2, x3, etc., then the probability that x will take that value is 0. So p of x will be 0 most of the times. And it will be non-zero, it can be non-zero only at points xk. So we are denoting the probability that x is taking the value xk by pk. Say the probability that x will take the value x1 is p1, etc. And we are representing this in the table form. So this is the PMF, another representation of our PMF. Here we are writing the values of x. So x1 is one of possible values, x2, x3 are possible values of x. Maybe this list is finite or infinite, countably infinite. And here we are writing corresponding probabilities. So here is the probability that x is taking the value x1. This x is placeholder for x1, x2, x3, etc. So this is the probability that x is taking the value x2. This is the probability that x is taking the value x3, etc. And usually we will write our PMF in this form. Sometimes we will give just by formula. Okay, so assume this is our PMF, probability mass function for our discrete random variable x. Then clearly these pk's are non-negative because they are probabilities. Usually we are not including in our list values with probability 0, but sometimes we include. So usually we will have the case when pk's are strictly larger than 0. And of course, the sum of all pk's will be 1. This is because we are covering here all possible values of x. We are not missing any possible value of x. So the sum of all these probabilities will give 1. Now one question, and you can try to answer that before listening to the continuation of this lecture. What is the difference between discrete probability models and discrete random variables? So in the case of discrete probability models, we were also drawing this kind of tables, but in that case we were including outcomes here, so outcome omega 1, omega 2, etc. And here we were writing just the probabilities. So probability of that outcome, let me write omega. So probability of that outcome omega 1, probability of outcome omega 2, etc. So very close to this, very similar to this, but there are some differences between this kind of tables and that kind of tables. Well, this table is for outcomes, and outcomes can be non-numerical, but we know that the random variable can take only numerical values, so x1, x2, x3 are some numbers, real numbers. Okay. Another thing is that for different outcomes, we can have the same value of x. So x1 can happen for different outcomes. Say in the darts game, we can have x is 0 in different cases. If I am hitting very far from the board, if I am hitting even farther from the board, etc. In all that cases, x will be 0. Okay. So let's move forward and solve a problem. So we have a box full of 10 red and 20 blue balls. So in general, in totality, we have 30 balls in our box, 10 red, 20 blue. We are picking at random a ball 3 times with replacement. So we are picking a ball, fixing the color, returning that ball to the box, and then shuffling, and then picking a ball again, and 3 times. So let x be the number of red balls among these 3 balls. So x is the number of red balls. The problem is asking, the example is asking to construct the PMF of x. Again, I'm suggesting you to stop this video and try to solve by yourself, and then return back. Okay. Okay, sorry, I need to go to the whiteboard. Nice, so to the whiteboard. First, because we have 10 red and 20 blue balls, the probability that we will have a red ball is 1 over 10 over, 30, which is 1 over 3, and the probability that we will have a blue ball is just 2 over 3, 20 over 30. Okay, nice. So x is the number of red balls among that 3 balls we will pick. So the possible values of x and probabilities that x is taking that particular value. So I can have the number x can be 0. So I can have no red ball at all in that 3 balls. Or I can have just 1 red ball. Or I can have 2 red balls. Or I can have all balls are red, so 3 red balls. Okay, nice. So now we need to calculate these probabilities. The probability that x is 0, meaning that no red ball happened. So because we are doing our experiment with replacements, we have independence in trials. So the probability that x will be 0 means that we need to calculate the probability that we will have no red ball. This is the same as to calculate the probability that all balls are blue. So the probability of having 1 blue is 2 over 3. So the probability of 3 times having blue is 2 over 3. So 2 over 3 cubed. So the probability will be 2 over 3 cubed. Okay, and this is when we are picking blue, blue, blue. Now, what is the probability that x will be 1? So the probability that x is 1 is in the case when one of the balls will be red and 2 others will be blue. So to pick a red ball, we have this much chances. So the probability of picking a red ball is with probability 1 over 3. Because of independence, I need to multiply by the probability of having 2 blue balls. And to pick 2 blue balls, the probability will be 2 over 3 squared. And sorry, I need to multiply this by 3. Why is this 3? This is because we have 3 cases of having just 1 red and 2 blue. We can have in this order red, blue, blue, or we can have blue, red, blue, or we can have blue, blue, red. So 3 cases, and for each case the probability of choosing that version is 1 over 3 times 2 over 3 squared. So we will have this formula. This is just a binomial formula, if you remember from our previous lectures. So 3 times 1 over 3 times 2 over 3 squared. Now, what is the probability that x will take the value 2? So this is the case when I have exactly 2 red balls. So 2 red balls and 1 blue ball. So the probability of that is the following. I need to choose 2 red balls, and the probability of choosing a red ball was 1 over 3. So 1 over 3 squared for choosing 2 red balls and 1 blue ball. This is with probability 2 over 3. And we have again 3 cases, and the cases are, so 2 red balls, red, red, blue, red, blue, red, or blue, red, blue. No, this is not correct. Blue, red, and another red, sorry. So here I will have 3 times 1 over 3 squared and times 2 over 3. And finally, the probability that x will be equal to 3. So this means that all balls are red. So to choose all 3 balls red, we have the following probability. The probability of 1 red is 1 over 3. We have independence, so we have 1 over 3 cubed. 1 over 3 cubed. So this is our PMF for that random variable. By the way, just quickly, let me erase some unnecessary part. This is not necessary now. Let me check that the sum of probabilities it will give 1. Okay. Sorry. Okay. Now I can write that. So take the pen. So I need to check that the sum of all this will give 1. So 2 over, this is 3. 2 over 3 cubed plus 3 times 1 over 3 times 2 over 3 squared plus 3 times 1 over 3 squared times 2 over 3 plus 1/3 cubed. This is 3. And this is of the form, let me write in this way, a cubed plus, this is a, 3 times, let me denote this by b, not blue, but b, b times a squared plus 3 times b squared, b squared times a, so a is 2/3, b is 1/3, plus b cubed. And from your high school curricula, you know that this is the formula for a plus b cubed. And this is called the binomial formula, in fact. That's why these probabilities are called binomial probabilities. So by using this formula, I will get b plus a plus b cubed. A was 2/3 plus b was 1/3 cubed, and this is 1 cubed, and it is 1. So this is a nice probability mass function, PMF. Okay, so let me erase this and go back to our slides. Now, one question: what will happen if we will consider the case when we are picking balls without replacement? So in this case, we will not have independence. So I'm leaving this to you. Try to solve that by yourself and draw the and construct the PMF of that random variable x. Again, another example with the same experiment. We are doing the same experiment, picking a ball from the same box with 10 red and 20 blue balls. But in this case, we are we are picking 3 times a ball, and we are fixing their colors. We are doing that with replacement, so we have again independence. Now in this case, we are considering another random variable, y. Y is the number of blue balls minus number of red balls that we will draw. So the problem is asking to construct the PMF of y. So let's go to our whiteboard. Okay. Sorry, whiteboard, where is my whiteboard? This is the whiteboard. Okay, so y was the number. Let me go back to see what was that number. Number of blue balls minus number of red balls. Okay. Blue balls number minus number of red balls. Number of blue minus number of red. Okay. And the probability of picking a blue ball was 2/3, and the probability of picking a red ball was 1/3. Okay, so what are the possible values of y? So we can have just 3 blue and 0 red. We are picking 3 balls, so we can have 3 blue and 0 red. In that case, y is equal to 3 minus 0, so y will take the value 3. Or we can have 2 blue balls and just 1 red. In that case, y will be the number of blue minus the number of red. It will be 1. The other case is when we will have 1 blue and 2 reds. And in that case, y is equal to 1 minus 2, and that is minus 1. And finally, we can have no blue ball at all. And in that case, we will have that y is equal to minus 3. So possible values of y are minus 3, minus 1, 1, 3. And just 4 values. So y is a discrete random variable. And the problem is asking to construct the PMF of that random variable y. So probability that y will take that particular value Let me just write y. Okay, -3, -1, 1, and finally 3. Okay, so probability that y is equal to, say, -3. Let me calculate that. Y is -3 only in the case when we have 0 blue and 3 red. So this is the same as 3 red. And we know that the probability of having 3 red balls is the probability of having just 1 red ball cubed, because of that independence. So we will have that this probability is 1/3 cubed. The probability that y is equal to -1 is the same as the probability that we will have 1 blue and 2 red. And we know how to calculate this probability. 1 blue and 2 red will happen with the following probability. To have a blue, we have this chance, this probability, 2/3. To have 2 reds, we have 1/3 squared, and we are multiplying them because of independence, and we can have 1 blue and 2 reds in 3 ways. So again, blue, red, 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 blue, red, and red, red, blue. So we will have 3 times 2/3 times 1/3 squared. The probability that y is equal to 1 is the probability that we will have 2 blue and 1 red, and you can calculate that, and the probability will be 2/3 squared times 1/3 and times 3. 3 times 2/3 squared times 1/3. And finally, the probability that y will take, sorry, I need to erase this, this is not correct. Okay, so the probability that y will take the value 3 is just the probability that y is 3 only in this case. The probability that we will have exactly 3 blue, and exactly 3 blue will happen with the probability 2/3 cubed. So we will have 2/3 cubed. So this is the PMF of our random variable y. Okay, let's move to our problem. Now, again, you can consider the case when we are dealing with the model without replacements. Now, recall that our main problem with random variables was to be able to calculate this kind of probabilities for any subset of R. So A is a subset of R, say A is some interval, and we want to be able to calculate the probability that X is in A. Now, assume that X is a discrete random variable, and this is its PMF. Using this PMF, we can calculate the probability that X is in some set A. And this is very easy. A is some subset, and we have the values of X, X1, X2, X3, and we are just looking at all values that are inside A. So if X1 is inside A, we are adding here P1. If X2 is not in A, we are not adding P2. If X3 is in A, we are adding P3, etc. So in general case, we are using this formula to calculate the probability that X is in A. So we are adding all probabilities pk such that the corresponding value xk is in A. In particular, if we want to calculate the probability that this random variable is inside AB in this interval AB, then we are adding all probabilities pk such that xk is between A and B. So if x1 is between A and B, we need to add p1. If x2 is between A and B, we are adding p2. If x3 is not in A and B, we are just skipping p3 and moving forward. Okay, we have learned two main characteristics of discrete random variables. So the first one was CDF, and CDF is working for any random variables, not only for discrete random variables, but for any random variables. But PMFs are for only discrete random variables. So I want to give some connection between CDFs and PMFs. So assume we have a discrete random variable given by this PMF, given by its values and probabilities of taking that values, and assume that f of x is the CDF of that random variable x. Then by definition, that CDF is the probability that x is less or equal than x. And we know already how to calculate these probabilities. Because this is the probability that x is between minus infinity and that small x. So this will be the sum of all pk's such that the corresponding values xk are less or equal than x. Now let's solve this problem. So what we have, assume I am picking a point at random from 0, 5 uniformly. So we are dealing with geometric probability case. If that point is less or equal than 2, then I am paying $5. If it happens that my point is between 2 and 3, including 3, then I am receiving $3. In all other cases, that is in the cases when my point is larger than 3 and smaller or equal than 5, then I am receiving $10. So paying $5, receiving $3, and receiving $10. Let x be my reward after just playing once. And the problem is asking to construct the PMF and CDF for this random variable. So let's start from the PMF. Okay, so I need to first draw the table. So the values of x and probabilities of taking that particular values. Okay. X is my reward, and I can either lose $5 or get 3 or get 10. So x can take only 3 values, minus 5, so minus because I am losing that, I am paying that, $3 or $10. Okay. So x is a discrete random variable because it is taking only 3 values, 3 possible values. Now let's calculate what is the probability that x will take the value minus 5, say minus 5. I will pay $5 if my point is less or equal than 2. So this is the same as to calculate the probability that my point is inside 0, 2. Why I am taking the 0? Because my point was from 0 to 5. So I need to calculate the probability that my point is between 0 and 2 if I am picking a point randomly from 0, 5. And because of that geometric probabilities formula, I'll need to calculate the length of 0,2 over the length of, well, let me denote that by 0,5. It is not so easy to write with this pen. So this will be 2 over 5. So the probability that I will lose $5, x will take the value minus 5, is 2 over 5. Now the probability that x will take the value 3. I will get $3, x will be 3 if my point will be inside 2, 3. So I need to calculate the probability of having a point between 2 and 3 if picking at random from 0, 5. So this will be the length of this interval, which is 1, over the total length of interval 0, 5, which is 5. So 1 over 5. We can calculate similarly the probability that x will take the value 10, but because we know that these numbers need to add to 1, I just need to calculate 1 minus 2 over 5 plus 1 over 5. That is, I will have 2 over 5. So you can check that the sum of all these three numbers will give 1. Now I have the PMF of this random variable x, and next problem is to construct the CDF, calculate the CDF of this random variable. And for that I will go to whiteboard. So where is my whiteboard? It is here. So again I'm writing that PMF x minus 5, 3, 10, and probabilities are 2 over 5, 1 over 5, and again 2 over 5. And let me recall that the formula for CDF, the definition of CDF, was the following. So we are calculating the probability that x is less or equal than that particular value x. Now let me just calculate several values. So what is the value of our CDF at minus 9? By definition, this is the probability that x is less or equal than minus 9. But we know that the possible values of x are just minus 5, 3, and 10. So no value of x will satisfy this condition, this inequality. That means that this set is, this event is empty. So we will have 0 just for this probability. And of course, if I will take x, which is less than minus 5, then f of x, which is the probability that x is less or equal than small x, our random variable is taking a value which is less or equal than x, will be 0. Why is this? Because x is less than minus 5 and no value e of x, capital X, is less than that x. Okay. Next, let me calculate the value of our CDF at minus 5, which is the probability that x is less or equal than minus 5. X is taking only these three values, and only this value will satisfy that inequality. Only in the case when x is minus 5, I will have that x is less or equal than minus 5. So I can just write this is equal to, this is the same as to have x is minus 5. And we know that this probability is 2 over 5. Only in this case we will have this inequality. Now it is easy to see that if I will take x between minus 5 and 3, then f of x, which is the probability probability that x is less or equal than x will be, okay, so this x is between -5 and 3. So in which case the value of x will be less or equal than that number. Say x is 0. If x is 0, for which case our random variable will take a value which is less or equal than 0. Only in the case when x is -5. So this is the same as writing x is -5. And again, this is 2/5. Now, continuing this way, we will find that if x is between 3, including that 3, and 10, then the value of our function f, our CDF, again, I'm writing the definition. This is the probability that x is less or equal than that x. This will happen in the following cases. So, I want to have that the values of my x, a random variable, are less or equal than that x. And x is, say, 4, or x is exactly equal to 3, or 4.5. I can have that x is, random variable x is less or equal than that small x only in these two cases. So if x will be -5, it will satisfy this property. If x will be 3, again, it will satisfy this property. So these probabilities can be decomposed into two cases. So either x is -5 or x is 3. And because we have disjoint events, so x cannot be both -5 and 3. I'm just writing plus sign. I'm just calculating the sum of all these individual probabilities. And this will give 2/5 plus 1/5. So 2/5 plus 1/5. Okay, and finally, if we will consider the case when x is larger or equal than 10, then the value of our CDF, which is the value, the probability that x is less or equal than that x, will be, so this is larger than 10 or is equal to 10, and we need to calculate the probability that x is taking values less or equal than that x. So all these values will be less or equal than x. So that means every time we will have this. So this is the sample space, total sample space. So we will have x is -5 or x is 3 or x is 10, and of course the sum of these probabilities will give 1 because we are considering all possible values for x. Okay, so finalizing, I can write that CDF in the following form. So it is 0 if x is less than -5. It is equal to 2/5 if x is between -5 and 3. So -5 less or equal than x is less than 3. It is equal to 2/5 plus 1/5, which is 3/5. 2/5 plus 1/5 if x is between 3 and 10, including 3, not including 10. And finally, the value of our f is 1, or which is the same, I'm just writing in this way, 1/5 plus again 2 over 5 for all values of x larger or equal than 10. So why I am writing in this way? To explain again the name CDF. CDF means cumulative distribution function. So this cumulative distribution function cumulates probabilities. So first we have 0 probability, then we are adding 2 over 5, then we are adding to that 1 over 5, then we are adding another 2 over 5. Okay. So let's move to our slides again. Sorry. I'm erasing this. Moving forward. Okay, another example number 2113. X is the number of heads shown when tossing a fair coin 4 times. So we are tossing a coin 4 times, our coin is fair, and X is the number of heads we will have. Then the first part is to fill this table, to fill this PMF. The values of X, number of heads, can be either 0 or 1 or 2 or 3, or we can have all heads. So 4, X is 4. And the probability that X will be 0, so no heads at all, means all values, or all outcomes are tails, 4 times tails. Because of independence, we will have the probability of 1 tail to the 4 and 1 heads and 3 tails. X is 1 means just 1 heads. That means 1 heads and 3 tails. And we will have with the following probability. So 4 possibilities for the place of that heads. So heads, then tail, tail, tail. Or we can have tail, heads, then 2 tails, etc. 4 possibilities. Then the probability of 1 heads, which is 1 over 2, and probability of 3 tails, which is, 1 over 2 cubed. 1 over 2 cubed. Okay, I will erase this and write, this is 1 over 2 to the 4. I can just write 1 over 2 to the 4. So let me write that. So 4 times 1 over 2 to the 4. Then the probability of having exactly 2 heads when tossing a coin 4 times. So we need to choose, sorry, this is not 6. We need to choose 2 places for heads, and we can do in these ways, these many ways. So in 6 ways we can choose the places for heads. Then we need to plug 2 heads there. So to have a head, we have 1 over 2 probability. For having 2 heads there, we will have this much probability. And then we need to have 2 tails, again with this much probability, and we need to multiply all this. So we will have this probability 6 times. If we will multiply this, we will have again 1 over 4 squared. Not 1 over 4, 1 over 2, sorry. 1 over 2 to the 4. Okay, the probability of having exactly 3 heads, because of symmetry, because our coin is fair, we will have the same as the probability of having 1 heads. So we will have here 4 times 1 over 2 to the 4, and the x is 4 in the case when we have 4 heads, and to have 4 heads we have this much probability. Okay, let me just erase this part, this calculation. Now we have the PMF of our random variable. Let's see what is coming next. Okay, calculate the probability that x is equal to 2. And the probability that x is equal to 2 is equal to, well, x is 2, the probability of that is 6 over 2 to the 4. This is the probability of having exactly 2 heads. Okay. The next problem is to calculate the probability that x will be less or equal than 2.5. So this is the case when we will have x can be less or equal than 2.5 only in the cases when x is either 0 or 1 or 2. So this is the same as to write probability that x is 0 plus probability that x is 1 plus probability that x is 2. Of course, we could calculate this by just calculating using complement. So this probability is equal to 1 minus the probability that x is larger than 2.5, and we will have 2 cases for that. Okay, it remains just to plug the values here to calculate this probability. So x is 0, the probability of that is 1 over 16 plus this is 4 over 16, and we can cancel them, but no need for that. And the probability of having x2 is 6 over 16. So 10, 11 over 16. Okay, so let's move forward. The next problem is to calculate the probability that x will be larger or equal than 1. And we can calculate in 2 ways. X is larger or equal than 1 means x is either 1 or 2 or 3 or 4, or we can just write this is by the formula of complement. This is the probability that x is, this is 1 minus the probability that x is less than 1, which is the same as 1 minus the probability x is less than 1 means x is just 0. X is 0. X is 0. So this is 1 minus 1 over 16, and this is 15 over 16. Okay, so we are moving forward. Graph the PMF of x. So in this case, we want to graph the PMF. Okay. Now let me erase and see what I mean by graphing that PMF. I'm erasing this part. I can just erase this part too, and this small thing. Now what I mean by graphing the PMF. So I'm taking that Cartesian plane. This is x. This is PMF axis. I'm changing the color. Say red color. Okay, so here I am placing on the x-axis, I am placing the values of x. So 0, 1, 2, 3, and 4. And for each point here, I am taking the value y to be the probability. So here are the probabilities. So PMF or probabilities. So the probability of 0 is 1 over 16. So this is 1 over 16. 1 over 16. For 1, the probability of having x being to be equal to 1 is 4 over, well, this is 4 over 16. So 4 over 16. This is 4 over 16. Or 1 over 4. For x equal 2, we will have 6 over 16. So another point over 2, this is 6 over 16. For 3, we will have again 4 over 15, so symmetric point here. And for 4, I will have 1 over 16, another symmetric point here. So this is the graph of PMF. And usually people are joining this by line segments. Well, line segments, of course. That was not so a line segment, but okay. So this is my graph of PMF for this random variable. Okay, so let's move forward. And now we need to graph the CDF of this random variable. Okay, so let me try to do that. Again, open that writing part, sorry. So this is my writing part. I'm erasing this part. I want to draw the CDF here, just here. Okay. So taking blue one for the axis. This is X. In this case, this is CDF. This axis will be the values of CDF. I'm taking a red. Now the graph of CDF. I'm putting here the values of our random variable 1, 0, 1, 2, 3, 4. Okay. So if x is here, then the value of our CDF is 0. Why is that? Because the value at this point for CDF is the probability that my random variable will be less or equal than that value, but my random variable is never negative, so it cannot be in this region. So the value of our CDF here is 0. So I will have constant 0 up to the point 0, not including 0. If I will calculate my CDF value at 0, that will be the probability that x is taking the value 0, 1 over 16. If I will calculate the probability that x is less or equal than 0.5, or which is the same, the value of our CDF at the point 0.5, then again I will get 1 over 16. So here I need to take 1 over 16, and I will have a constant function with the value 1 over 16 from 0 to 1, including 0 but excluding 1. Then if I'm taking a point here and want to calculate the value of our CDF at that point, so say 1.7 or 1.6, the value of CDF at 1.6 is the same as the probability that x will be less or equal than 1.6 or 1.7 or 1.5, and we have only two cases, 0 and 1. So I need to add these probabilities to have the value of our CDF at this point or that point or that point. So we will have a constant function here from 1 to 2, including 1 but not including 2, and this point will be the sum of these probabilities. So 1 over 16 plus 4 over 16, this will be 5 over 16. And importantly, this jump size is 4 over 16, and the jump size is this probability. Okay, moving this way, we can calculate the values of our CDF at all points. So from 2 to 3, if I will take another value here and try to calculate the value of our CDF at that point, I need to add these 3 probabilities, because my random variable will be less or equal than that point only in the cases when x is 0, 1, or 2. So I will have another jump with size. So jump is 6 over 16 is equal to that probability, and this point will be, if I will add 6 over 16, I will have 11 over 16. So again, from 3 to 4, I will have a constant. I will have a jump here. Jump size will be this probability, 4 over 16. And this point will be, if I will add 4, I will have 15 over 16. And from 4, starting from 4 and up to plus infinity, I will have constant 1. Because in that case, I need to add all these probabilities, and the sum of all these probabilities will be 1. So this is 1. So this is the graph. By the way, this jump size is 1 over 16. So this is the graph of our CDF for this random variable. Okay. So I'm erasing everything. Yeah, we have finished with that example. So our next example is the following. We are tossing a fair coin until it will land on heads. X is the number of tosses we need to do to have heads. So X can be 1, at the first try we have heads, or X can be 2, meaning that the first toss was tails and the second was heads, etc. And the problem is asking for us to construct PMF of X, PMF, then calculate the probability that the first head is on the third toss, calculate the probability that the first 2 tosses are tails, and calculate the probability that we will do even number of tosses until having heads. Okay, let's solve gradually. So I want to open whiteboard, erase everything. Okay, so X is, okay, I can change the color. X is the number of tosses until having heads. Okay. So this is the PMF table. The probability that X will take that value, particular value X. So X can be 1. X can be 1. X is 1 means that the first toss was heads, and we are stopping there. We are finishing tossing coins. And the probability that X is 1, or having the first toss heads, is 1 over 2, because we are dealing with fair coin. X can be 2, meaning that this is, let me write the outcome, heads. 2 means that we are doing, the second toss was heads, but the first was tail. So tails, then heads. And the probability of having this outcome is 1 over 2 for tails times 1 over 2 for heads. We are multiplying because we have independence in the tosses, and I will have 1 over 2 squared here. We can have that x is equal to 3, meaning that first two tosses were tails and the last one, third one, is heads. So we are stopping at the step number 3. And the probability of having this outcome, or the probability of having x3, is just 1 over 2 to the 3, 2 cubed. Then next is 4. This is when tails, 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 heads, and the probability of that is 1 over 2 to the 4, etc. The general formula here will be for k, say, if x is k, we will have t, etc., t, and this is k minus 1 times, and then heads. And for having this outcome, or for having x to be k, we will have this probability 1 over 2 to the k, etc., etc. So this will go to the infinite. So in this case, we have a discrete random variable with infinite range, but countably infinite range. Of course, we can write this in the compact form. This PMF can be written in the compact form. The probability that x is equal to k is 1 over 2 to the k, and k is any natural number. So this is the PMF, another form of PMF. Well, personally, I'm preferring this table form. Okay, so let's move back to see which problems we need to solve concerning this example. So what is the probability that we will have the first heads on the third toss? So first heads on the third toss. So this is the same as to write x is equal to 3. Third toss was heads. Okay, and we know that this is equal to 1 over 2 cubed, which is 1 over 8. Okay, let's go back. What is the probability that the first two tosses were tails? First two tosses were tails. Okay. In this case, the first toss was not tails, so this is not satisfying, this is not satisfying. In this case, the first two tosses were not tails, the second one was not tails, so this is not satisfying. This is satisfying because first two tosses are tails. This is again satisfying, so first two tosses are tails, etc. So starting from this point on, all values of x will satisfy. So the probability that first two tosses are tails is the same as to write the probability that x is larger than 2. It's the same as to write the number of tosses, total tosses until heads, is larger than 2. And we can calculate this either by summing all these probabilities starting from 1 over 2 cubed, and then 1 over 2 to the 4 plus etc. up to infinity, or we can just write by using that complement formula. This is equal to 1 minus probability that x is less or equal than 2, and this is equal to 1 minus x will be less than or equal to 2 only in the cases when x is 1 or 2. So probability that x is 1 and minus the probability x is 2. Or I can write in this way, maybe it is better to write in this way. And this will be 1 minus 1 over 2 minus 1 over 4. So I'm adding these two probabilities. Okay, this is the probability that first two tosses will result in tails. Okay, so and the last question is, what's the probability that we will do even number of tosses? So x will be an even number. So let's go to the whiteboard. So we are asked to calculate the probability that x is even. The probability that x is even is the same as the probability that x is 2 or x is 4 or etc. X is 6, x is 8. So we will have this formula 1 over the probability that x is 2 is 1 over 2 squared plus 1 over 2 to the 4 plus etc. And we can write in the compact form, in the form of a sum, 1 over 2 to the 2k, and k is running from 1 to infinity. K is running from 1 to infinity. And this sum will be, this is a geometric series, and the first term is 1 over 2 squared, and the ratio is again 1 over 2 squared. So this will be the probability that x is even. Okay. Another question, another problem for this example. We need to graph the CDF of x. Okay. So let's open that whiteboard. So I need to graph the CDF of this random variable given by this PMF. Okay, so let me erase this part. So let me just increase the size. Okay. Nice. So we need to graph the CDF. Try to draw the graph of PMF by yourself. Okay. So this is CDF and this is X. Okay. Now I am placing the values of our X in this axis. So this is 1, this is 2, this is 3. X can take the values 1, 2, 3, 4, etc. Okay, and the value of our CDF will be 0 until this point 1. Why is that? Because if I will take this value and try to calculate the value of CDF at that point, the CDF at that point is the probability that my X will be here. But X cannot be here because X is taking the values 1, 2, 3, 4. So up until the point 1, I will have 0. So starting from 1 and until 2, I will have a constant which is equal to this probability. So I have a jump at the point 1. Jump size is, this size is 1 over 2. And the value is 1 over 2. So this size is 1 over 2. Let me just try to write 1 over 2. Okay, starting from 2 and up until 3, I will have another constant. Jump size is this much, so this jump size is 1/4, and this value is 1/2 plus 1/4. We are accumulating the probabilities. Okay, next one is at 3 I have a jump of size 1/8, and I have a constant CDF, constant function for CDF until 4. So this jump size is 1/8. This value is 1/2 plus 1/4 plus 1/8. So I'm accumulating the probabilities, and so on. I will have another this type of thing and that type of thing. This will tend, of course, at plus infinity, the sum will tend to 1. If you will add all these probabilities up to infinity, you will get 1. So this is the graph of my CDF of this random variable. Okay. Let me see what is happening here. Okay, now I can move that. We have drawn different CDFs for CDFs for different random variables, and we have seen that CDFs of discrete random variables are piecewise constant or step functions. So this is true for any discrete random variable, and I want to give the general idea how to construct this graph of CDF for a discrete random variable. Assume we have a discrete random variable given by this PMF. So values of x and probabilities of taking that particular values. Then the graph of CDF will be a piecewise constant function, or otherwise step function. The jump points will be, the jump of CDF will be at these points, and the jump sizes will be at x1, the jump size will be p1, at x2, the jump size will be p2, etc. And of course, because we have a CDF, CDF needs to be continuous from the right at every point. And I will give the graph here on my whiteboard. So let me open that whiteboard, erase everything. Okay, so axis again, something like this. Okay, then I will change the color, say x1. Here I am putting the values of possible values of our random variable, etc. Say x4, x5, maybe infinitely many of them, silently assuming that xk's are in the increasing order, of course. So I will have 0 up to this point. Then we will have a jump. This is CDF. Let me specify that I am drawing the graph of CDF, and this is x-axis. The CDF will have a jump at the point x1, and the jump size will be p1, and another jump at the point x2, and this jump size will be p2. So this point is just p1, this point is p1 plus p2, because I am adding 2 jumps of sizes p1 and p2, etc. Another jump here, jump size is P3, and this point is P1 plus P2 plus P3 until the point x4, etc. So we will have step function with jump points at the values of random variable x and the jump sizes as the probabilities of corresponding values. So the jump size at the point x2 is P2, etc. So this is a general idea to construct a cumulative distribution function for a discrete random variable from its PMF. Okay. Now let's solve the inverse problem. Assume we have the graph of CDF of our discrete random variable. So we have some graph of piecewise constant function, and we want to construct the PMF. In general, the PMF is constructed in this way. This is correct. This is true for any random variable. This was the property of our cumulative distribution function, CDF. But of course, most of these probabilities, most of the times, for most of the values of small x, these probabilities will be 0, because f will be continuous at most of the points. Okay, so it will be non-zero only at values of our random variable x. If xk's are the values of our random variable x, then the probability that x is taking the value xk will be the jump size of our CDF at that point xk. And graphically, CDF will be a piecewise constant function, of course, increasing function, right, continuous, and the possible values of x are the jump points, and the probabilities that x is equal to xk will be the probability that x is equal to xk will be exactly the jump size at xk. And the graph is the following. Let me give, well, I have an example. I will give it using this example. So what we have here, yeah, okay. So below we have a graph of CDF of some random variable x. I want to construct the PMF of x. So PMF of x means I need to give the values, possible values of x and probabilities of taking that values. X is equal to that small x. Okay, so what are the values of our random variable x? Exactly the jump points. So our function has a jump at point -2, has another jump at 1, and another jump at 3. So it means that the possible values of x, our random variable, are -2, 1 and 3. So these are the only possible values of our random variable x. And what is the probability that x will take the value -2? To calculate that probability, I just need to calculate this jump size. And this jump size is, this is 0, this is 0.3, so the jump size is 0.3. So 0.3. Okay, to calculate the probability that x is equal to 1, so this is 1, I need to calculate this jump size. And this jump size is, this value is 0.7, and this is 0.3. So 0.7, 0.3, and the jump size, this difference is 0.4. So we have 40% probability that x will take the value 1. And finally, I can calculate this by a jump size, or just by calculating 1 minus 0.3 minus 0.4, which is again 0.3. So this jump size is 0.3, and we can check that. This is 1, and this is 0.7. This is 0.8, this is 0.7, so the jump size is 0.3. So this is our PMF read from the graph of CDF. So summarizing, in this lecture we have learned that a random variable x is discrete if it is taking only finitely many values or countably many infinite values. We have learned that we have two complete characteristics for discrete random variables. And the first one is the CDF and the second one is PMF, probability mass function. In fact, CDF is working for any random variables, not only discrete but all random variables. But PMFs are specific to discrete random variables. Having either of them, having CDF or PMF, we can calculate this kind of probabilities for any set A. And the graph of a CDF of a discrete random variable is a piecewise constant function, and the jump points are exactly the values of x, and the jump size at some point is the probability of taking that particular value. Later on we will talk about very important discrete random variables. I will give examples of very important discrete random variables. In particular, we will talk about Bernoulli, binomial, geometric, Poisson random variables, and maybe about some other discrete random variables too. So this is all I wanted to give about general theory of discrete random variables. Next time we will continue talking about the second type of random variables, about continuous random variables. So thank you, be healthy, take care.